All right. Well, thank you to the organizers for uh, putting this event together. It's been fantastic so far. Um, and well, thank you also for giving me the opportunity to present this work. This is work joint with Philippe Nadeau at Lyon. So, all right, let me see if this is this. Oh, 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 it's supposed to be working, but okay. So here's the big picture version of the talk. So I have a very narrow focus, so very singular vision. I want to compute the class of a certain subvariety of the complete flag variety. This subvariety is the permutahedral variety. So that's the geometry / topology version of the question. Thanks to work of several fantastic mathematicians, we can turn this into algebra. And the first level that I'll go down is travel back in time to realize that this is a question you could have phrased in the language of Postnikov's work on volumes of permutahedra with this operation called divided symmetrization. And then we'll go further back in time, 2 years further. Turns out you can cast that operation as a computation in the polynomial ring modulo the ideal of quasisymmetric polynomials. Okay? And this talk is really me trying to convince you that there's some interesting behavior in this particular polynomial quotient, some nice combinatorics. And to this end, I will introduce a basis of the polynomial ring that I call Forest polynomials. Okay, so this talk is largely about the combinatorics of this new basis. All right, so this is the big picture. Let me just zoom in a little bit. Like I said, the main protagonist is polynomials modulo quasisymmetric polynomials. I'll define these guys. You should think of this as the quasisymmetric analog of a space that you hopefully know and love at this stage. Then I'll phrase the Schubert positivity question that I'm interested in, and actually answer it immediately through a combinatorial procedure, and then tell you what's behind the scenes. Okay, so what's the works? Well, this is really the topic of interest. Okay. Right. So what's a quasisymmetric polynomial? You know symmetric polynomials. So this is a mild generalization. A polynomial p in variables 1 through n is quasisymmetric if the following holds. You hand me a sequence of positive integers, alpha 1 through alpha m. Then the coefficient of x1 to the alpha 1 through xm to the alpha m in P equals the coefficient of x sub I1 to the alpha 1 through x sub Im to the alpha m for any strictly increasing sequence of m indices. So, sounds long, it's not so bad. So here's a quasisymmetric polynomial in 3 variables. The indices are always ordered in increasing order, so you notice the exponents are the same, and so are the coefficients 2, 2, 2, and this has coefficient 1. So this is a quasisymmetric polynomial. In particular, symmetric polynomials are certainly quasisymmetric. All right. So here's my quasisymmetric analog of an ideal you care about, or you care about when you do Schubert calculus. I'm going to take the ideal generated by quasisymmetric polynomials, and they'll have constant term 0. You get some ideal. And this is what Jean-Christophe Aval and Nontel and François Bergeron studied in 2003. And one could ask, well, why would you do this? Well, this has a famous cousin. Right? This is the ideal of symmetric polynomials. And this quotient, the coinvariant space, well, here's at least 2 reasons to care about it. It's the cohomology ring of the complete flag variety, and it's, if you're a representation theory-minded person, it's an n factorial dimension vector space which carries a graded Sn representation, the regular representation, no less. So this inclusion of symmetric polynomials inside quasisymmetric polynomials is this inclusion of ideals implies an injection between this quotient on the left and this quotient on the right. And if the quotient on the right is shiny, one hopes that the sheen rubs off on the guy on the left. Okay? That's sort of my naive hope. All right, so here's here's a pretty picture already. So here's the description that I'm going to call the ABB decomposition. So this is what Walker and the Bergeron brothers did in 2003. Here's a set of sequences of length n, and here's the condition on these sequences. If you look at the tail of a sequence, a tail of length k, then the sum of the entries is going to be strictly less than k. So here's B sub 3. If you look at any tail and add the entries in the tail, the sum's less than the length. This is a prototypical Catalan object, right? This is one standard Catalan object. So this is 5 for Catalan 3. And the decomposition theorem says the polynomial ring splits into two pieces, one the ideal of quasisymmetric polynomials, and then there's a piece that is Catalan dimensional, and it's spanned by the monomials corresponding to these guys. Okay? So C is supposed to be the exponent vector. So 2, 0, 0 will produce x1 squared, 1, 1, 0 will produce x1, x2, and so on. Okay? So already nice picture in that this quotient is, as a vector space, Catalan dimensional. And this monomial basis is going to play a key role. So this was the result that was proved, and for a fair bit of time, that was the only result that was proved about this particular quotient. Any questions at this stage? Okay. So let me tell you what my oh, this is better. I see. So let me tell you what the Schubert class expansion that I'm interested in is. Already this picture appeared in Anna's talk, so here's a crash course in case you missed that talk. But right, so what's my context? The complete flag variety contains a distinguished set of Schubert varieties which have classes, Schubert classes. They span the cohomology ring. And now I get to play my standard game. For any subvariety inside this guy, you can ask for the expansion of this class in terms of Schubert classes. Right? And for geometric reasons, that these are intersection numbers, you know that these coefficients that come up are going to be non-negative. Well, if you don't like to do the geometry aspect of things, here's the polynomial version. Borel tells you that this cohomology ring is really this quotient, and then the classes become Schubert polynomials, which also appeared in Anna's talk. And then this question about Schubert positivity translates to a question about polynomial ring. If you have the polynomial that represents the class of your favorite subvariety, then you can ask for the Schubert expansion, and these same coefficients are going to show up here. And now you're in polynomial world, and hopefully, or maybe you're more comfortable in this setting. And this is the setting I'll work in. Okay, so now you have a steady stream of Schubert positivity questions, and I'm going to pick the permutahedral variety because turns out this was hard enough for us already. Okay. So this variety is a smooth toric variety of dimension n minus 1, and Dave Anderson and Juliana Timochko already gave us a polynomial representative for this class. It's this product on the left-hand side, right? So mindful of the indices, J and I differ by at least 2. So it's like a Van der Monde determinant, but it's missing stuff. And the stuff it's missing is xi minus xi plus 1. Right? And the question that I was asking on the previous slide about the class of the permutahedral variety is really this question. Right? I want to take this thing, and I want to expand it in terms of Schubert polynomials of degree, co-degree n minus 1. And they're going to come up with some coefficients which are non-negative. Yeah. Yes. Oh, sorry, this doesn't work for some reason. There you go. No, I didn't. I sort of wanted, but I can tell you later what it is. It depends on a choice taking a diagonal matrix and then acting on a flag, and you want an inclusion of flags. I didn't define it, but It's a nice variety, and I can tell you more later, but sort of doesn't concern me immediately, which is why I'm. Other questions? Okay. All right. So that's the question I want to address. I want to say one more thing already. This is a specialization of a double Schubert polynomial. So if you know Cauchy's identity, you can expand this as a product of Schubert polynomials, and hopefully you've been convinced enough in the last few days that that's a hard question, right? Or can be. Yes? Yes, please. There you go. So that was for any subvariety? No, they're not. Oh, they're the same guys. So all I'm doing is transforming this class computation working with Schubert classes and class of a variety as a polynomial question. You hand me the class of a variety as a polynomial inside this guy, and I can express it in terms of Schubert polynomials. The same coefficients will show up. That's how I know beforehand that they're going to be non-negative. Yeah, so maybe let me just, okay. So what I'm trying to say here is maybe I should write something on the board. So if you take n equals 3, then the guy on the left is x1 minus x3. If you're working modulo with n equals 3, this is really congruent to x1 plus x1 plus x2. And hopefully you see two Schubert polynomials. So these would be the intersection numbers had you actually worked that out on the previous slide. Other questions? Okay. Right, so these are the quantities of interest, these A sub W's, and they'll occupy me for the rest of the talk. So here's the first transformation, turning this into a question that I can tell a computer to do the heavy lifting. This operation of divided symmetrization, you take a polynomial, and here's what you do. You divide it out by this product of xi minus xi plus 1. Now you've got a rational function, degree, and then you symmetrize this expression. You hit it with the symmetric group, you get a bunch of rational functions, add those up, and it is what it is. That's what I'm going to call the divided symmetrization of f. Okay? So a pest to compute by hand, but your computer's happy to do it. And if the polynomial f has degree n minus 1, then the result is a scalar. Right? You've got something of degree n minus 1 above, degree n minus 1 below. You symmetrize, it ends up in the ground field, so it's a scalar. It's got no variables involved. Okay? So my A sub w, the coefficients of the Schubert polynomials in the class of the permutahedral variety, can be computed by this painful procedure. You plug in f equal to a Schubert polynomial, compute the sum, and that's a number. Turns out it's a non-negative integer for geometric reasons, and hence the question. We'll explain this combinatorially, and we were not the ones to come up with this expression. This was already used by Postnikov in his work on volumes of generalized permutahedra. This is what he uses to compute or give expressions for certain volumes. Okay, so I want to answer this question combinatorially, and to that end, I will need, yes, please. So, okay, so maybe, it's really going to be equivalent. So what I'm doing instead is hitting with the Schubert of the appropriate degree and performing a complete anti-symmetrizer. I'm applying the divided difference of the longest word, which is exactly why this symmetrization shows up. Yeah. Okay, so there's a little bit of work that goes into this, but it's exactly as Alex said. Okay, so let me tell you how to compute these A sub w. There's going to be a parking function flavored thing going on here, and then I can explain why it shows up. Okay. So here's my setup. There's going to be parking spots labeled by the integers. And there's going to be n cars, each having a preferred parking spot. And here's going to be an intermediate scenario. Say you know how to run this algorithm and you've reached an intermediate stage. Here's what an intermediate stage will look like. The cars, the occupied spots are going to decompose into intervals, and which I'm going to call I1 through Ik. And every interval is going to have one distinguished spot. Okay, so one marked spot. So here, these are my 3 cars, unicycles even, and the 0 and the 5 and the 10 are the marked spots in that particular interval. Okay, and the marked spots will play a key role. Okay, so here's the actual procedure. Here's the move. You've parked k cars already. You're at some intermediate stage. Car k plus 1 comes in. It has a preferred spot P. Well, here are the rules. If the spot's free, take it. Otherwise, the spot's occupied. If the spot's occupied, look at the entire interval of occupied spots, and now you're going to make a choice whether to keep going down or whether to turn back and take the spot on the left extreme or the right extreme. Okay? And what governs that choice? Well, you compare your preference to the marked spot. If you exceed the marked spot, you go right and take the right extreme. And if you're strictly less than the marked spot, you turn around and go to the left extreme. Okay? And then you remember your choice of the previous marked spot. Okay? So P is going to be the unique marked spot in this enlarged interval. Right? So when you've parked your car at one end, your interval's grown, and the marked spot can change. Okay? The preferred spot becomes the marked spot. So I'll do an example which will hopefully tell you what's going on, but do ask me questions. Here's my word to be read, left to right. So 5 is the first spot. Everything's free to begin with. So 5's taken, and 5's marked. Once the next car, one's free, so it gets taken, and it gets marked. Next up is 4. Right? So when 4, it's free, but now the interval's grown, and the marked spot, the preferred spot, must be the new mark. So 4 becomes the marked spot in that interval. Same for 2. It's free, but the interval grows, and the mark shifts. Here's another 2. What happens? This car, the 5th car, wants to park here. It's occupied. So it compares itself with the marked spot. It realizes it's weakly larger, so it goes right and ends up here. Did I? Because the 2 was the preference. So it remembers the past, yeah. No, thank you. Yes, it's a little, it will feel contrived for a reason, and my hope is to tell you that it looks contrived, but it's a shadow of a more, okay. And then finally the 3. So whatever's highlighted here will certainly be marked here. Okay? So the 3, it compares itself with the 2 again and decides to go right. And the spots 1 through 6 end up getting filled, and there's a unique marked spot in that interval. Questions? Right. Thank you. That's yeah. Other questions? Yes. This guy? Yeah. So here is the intermediate stage, and this 5th car wants to park here, right? So it sees that it's taken. When it sees that it's taken, it compares itself with whatever the marked spot is in that interval and goes away from it, as Alan put it. So it can't park here, so it goes to the other free spot that's immediately free. So here that's the 3, so that's that. Yes. Yeah, had it been 1, it would have turned around and went to the left extreme, right? Had this guy been a 1, it would compare itself with the 2, sees that it's to the left, so it would go in that direction. Okay, so obvious definition coming up. If you've seen parking functions before, I call a word an omega parking word if the occupied spots end up forming an interval, and park n is going to be omega parking spots of length n. Here are the first 3 three sets, and they have the cardinality n plus 1 to the n minus 1. And if you've seen Pollack's proof of the parking function counts, this should not be a surprise. Okay? So the ability to reverse your car doesn't matter if you're working on the circle, and the classical proof of Pollack actually works on the circle. Okay? So you get the same nice enumeration in spite of this fairly involved parking procedure. Right, so here's a theorem that answers that Schubert positivity question I had at the very start. If you want to count a sub w, which was the coefficient of a Schubert polynomial, well, you start with reduced words for w inverse, perform this procedure, and if you get an omega parking word, that contributes 1, otherwise the reduced word contributes 0. So words that park contribute to a sub w. Okay. And so if this was w equals 21543, length 4 permutation living inside S5, it has 8 reduced words, and the first 4 are parking words, and the remaining 4 are not. So a sub w equals 4. Okay. Right. So here's the natural question. Yes. Okay. So maybe let me try and do this here then. So here's, say, spot 1, 2, 3, 4. 1 goes here, right? Then the 3 comes, it takes this spot. The 4 comes, it's taking this spot, but this is the marked spot. And now the 3 wants to park in this interval, so it has to go away from it, right? So the last car has choice 3. It wants to park here, but the spot's taken. Then what's the criterion? Compare yourself with the marked spot. If you're less, go left. So it ends up taking, so the car 3 ends up sitting right here, and then take over the entire interval. Right, so really the question that stands is, I describe a sub w as a rational function, sum of rational functions. It's collapsing nicely to this quantity, which begs the question, why is that the case? And that's what I'll explain next. All right, so what's tying divided symmetrization and quasisymmetric polynomials? Here's a lemma that we proved, sort of serendipitous. It was not in any way clear that quasisymmetric polynomials have something to do with this, but here it is. If you hand me a polynomial of degree n minus 1, I can break it into its 2 pieces thanks to this ABB decomposition. There's the quasisymmetric chunk in red and the good stuff in blue. And the idea is that the divided symmetrization of F is an evaluation of the good piece, G, at the all ones vector. Right? So you're specializing xi equals to 1. You're essentially summing the coefficients. So I can turn this task, which is a rational function operation, into a coefficient, sum of coefficients business. And that's essentially what we will do to compute the divided symmetrization of Schubert polynomials, and to explain its non-negativity, find a way to split this Schubert polynomial into its good piece and the red piece. And if all goes well, then the good piece has positive coefficients. Just sum the coefficients, and that's your positive quantity. Okay? So this is a strategy. One could argue that praying is not a good strategy, but I beg to differ. I think it's the oldest strategy, right? And occasionally it works. Correct. Yeah, I should have used that. Thank you. Okay, so right. So let me just what's the word? Recapitulate. Yeah. Tell you the strategy again. I'm going to try and find a basis of the polynomial ring that is friendly to my goal, right? Reduction modulo QSIM, and splitting it into this thing should be an easy task. And then I want to do a principal specialization. So my hope is find some basis that behaves nicely with respect to the first step and has a good principal specialization. Any questions before I proceed further? So now I can define the polynomials that play a key role. So the combinatorial data structure is what we call an indexed forest. Okay. Maybe I should at least try and say why one should think like this. You have a Catalan dimensional space, and you wanted to do something with quasisymmetric functions / polynomials. A good source of quasisymmetric functions / polynomials are posets, and they're p-partitions generating functions. And a good source of Catalan objects are trees. So if you want the two of them together, then trees can feel like posets. And then you want to take p-partition generating functions. And that's sort of what I will try and mimic here. Okay? So my indexed forest comprises of this data, the data S, which is going to be a bunch of positive integers, which I'm going to split into intervals. Okay? And for each interval, I will have a binary tree with that many nodes. The size of the interval, that's going to be the number of nodes. Okay? So here's S, the support. I split it into intervals. That's 2, 3, 4. That's 7. And that's 11, 12. Okay? So maybe I should say this. I'm labeling the unit intervals by 1, 2, 3, and so on. Okay? Whereas the forest here, well, it's sitting on top of these intervals. Right? So here's a forest with 3 nodes. These crosses are going to be the leaves, so it feels like a complete binary tree. Here's a forest sitting on top of the 7, and here's a forest sitting on top of that interval. Okay? So couldn't resist some death rays, if you will. And to tone down the aggression, they're dotted. Right? So these, what is the point of this interval? Well, it's really just addressing the nodes of the tree, right? If you know in-order traversal of trees, the 2 is sort of in bijection with this node, the 3 is in bijection with this guy, and so on. Okay? So the entries of the interval essentially address these nodes as you read from left to right. Okay? So it's the canonical labeling of the nodes up to a shift. There's going to be a flag. So I'm moving towards polynomial land. There's going to be a flag associated with an indexed forest. You look at every node whose left child is a leaf, so this guy, and look at what interval it sits above. That's a 2. And then you go all along to the left and label the nodes along that path with 2s. So this is a 2, and that is a 2. And this has a left child a leaf, label it with a 4. This has a left child a leaf, label it with a 7. And then you go to 11s as well. So indexed forest and a flag. And finally, a composition which counts how many entries of each type in the flag, right? So there's 2 2s, so C2 is going to be a 2. There's 1 4, then C4 is going to be a 1. C1 and C3, no 1s, no 3s in the flag. Those are 0s. Right, so here's my bijection. Any indexed forest is the same data as a code. So I'm just transforming the code of a permutation into this indexed forest. So this is a bijection between codes, lemur codes, and indexed forests. So anything that's indexed by codes can be now indexed by indexed forests. Schubert's can be indexed by codes. If you read Lascaux, they are. So this is also something that's indexed by codes. Questions? Okay. All right, so I'm going to cook up polynomials, so I need to attach monomials. The monomials have to obey the following conditions. They have to respect the flag. So at every internal node, the integer I assign cannot exceed the bound imposed by the flag. Furthermore, they increase strictly as you go along right edges. So if you go to the right, going down, then they increase strictly, and if you go to the left, they increase weakly. And with any such labeling is attached the obvious monomial. Right? Take x sub kappa v over all nodes in your forest. Yes? Oh, yeah, sure. So Johnny's question, how do you get row f? So I scan this thing from left to right. Okay, so this is perhaps an easier way. Find the first node whose left child is a leaf. So this, for instance. And then you look at which unit interval it sits above. That's the label it gets. So this guy gets a 2. And then I go all along the path above it and label everything on that path with a 2. And then I proceed. Okay? And these runs then are encoded in this vector, and that's the code. Okay? All right, so I'm attaching a monomial, and then you see this obvious definition coming if you've done enough combinatorics. The forest polynomial, you're going to attach, you start with an indexed forest, take all monomials that respect the flag and the conditions on this earlier page, and this is going to be a result. This polynomial is the forest polynomial attached to this tree. Okay? So A and B can never exceed 2 because that's the flag. C cannot exceed 4. I am increasing, strictly increasing going right, so B is less than C, and I'm whatever's the right inequality, your inequalities are weak to the left and strict to the right. So this is an sum of 8 monomials. It is, in fact, a Schubert polynomial. I'll let you figure out which one it is. It has a leading term in the Revlex order. And you perhaps recognize the leading term. It's essentially the code of the indexed forest. So this has code 0, 2, 0, 1. That's that, which tells me this is a basis. So now I've got a basis for the polynomial ring indexed by indexed forests. Here's me splitting this sum of 8 polynomials into 2 chunks, and this is to tell you where this is going next. These are both slide polynomials, and that's what I'm going to define. Okay, so I'm not really sure if slides polynomial showed up in the lecture course, but okay, so here's, so these guys sum up 2 Schubert polynomials, so they're constituents of Schubert polynomials. What's my definition of a slide polynomial? You hand me a word in the alphabet Z, so hand me a bunch of positive integers, and I'm going to define a set of compatible sequences. What does this set contain? It contains things that are weakly decreasing, read from left to right. And the further condition is, they're bounded by the ij's, right? So these guys tell you how large each of these entries can be. And anytime the sequence I drops, the sequence A must drop as well. So the sequence A sort of follows the word I. Okay. And the slide polynomial is indexed by this word I, and it's the sum of monomials attached to elements of compatible sequences. Okay. So some polynomial. And with the definition I've given, this polynomial is either 0, you might not have any compatible sequences, or when it is equal to something which is non-zero, it is a slide polynomial as defined by Sami Asaf and Dominic Searles. Okay? And then you can index it by a weak composition. How'd you do that? Well, look at the Revlex leading term. So Schubert polynomial is a sum of a bunch of these guys. So let me tell you that forest polynomials are coarser than slide polynomials. So they're a coarsening of slide polynomials, and how do you do that? You treat your forest as a poset. So it's a Hasse diagram of a poset, and you look at its set of linear extensions, decreasing labelings, if you will. If these are the nodes, assign a word by looking at the flag attached to each node. Now read the nodes according to your linear extension. That determines this word IL. This word IL in turn determines a slide polynomial. It could be 0. And then you sum over all these linear extensions. That's the forest polynomial. Okay. And if you've seen Stanley's theory of p-partitions, this is not a surprise. Right? This is me just working with the polynomial analog, and in fact following Asaf and Bergeron in their work on flagged Thero partitions. So just as an example, the same polynomial from before, it's a sum of 2 slide polynomials, one for each linear extension. Here's one extension, you read the flags, right? So 4, 2, 2 corresponds to this, and 2, 4, 2 corresponds to this linear extension. Yes? This might be misleading because it feels zigzag, the moment it starts to have an actual, right, this will turn out to be one because of this. It feels like a hook. So if you work with trees that have this sort of a linear structure, it will be flat shoes. But the moment they have more interaction, I don't think it turns out equal flat shoes. Yeah, why am I focusing on trees? Well, if you have forests, this basis is multiplicative. So I can just work with the trees, and that's fine. So I was interested in reduction modulo QSIM, and this is why we introduced this basis. Well, what's the good thing about this basis? Reduction modulo QSIM is sort of a joke. It's where you can read it from the indexed forest. What's my theorem? It's succinct, but it actually takes some work getting here. Forest polynomials either lie in the ideal of quasisymmetric polynomials, or they're a bunch of good things, right? So they're a bunch of ABB monomials, as I've been calling them. So what determines whether they lie here? Well, you look at the support. So your forest is supported on some intervals. If the support is not this, 1 through n minus 1, then the thing lands inside the ideal. And if the support is precisely a subset of 1 through n minus 1, then it needs no reduction. So you should compare this with Schubert polynomials. If I hand you a Schubert polynomial indexed by a permutation is in S infinity, and you reduce it modulo the ideal of symmetric polynomials in n variables, then it's either 0 if its last descent is at position n or above, or it needs no reduction. It's already a linear combination of Artin monomials. What am I trying to tell you? ABB monomials should really be treated as Artin monomials for the sake of things that I am trying to do. Okay? So turns the task of reduction into a task of testing what the support is. So here's 3 forest polynomials. They're translates. So here's the slide polynomial 201. N is 5, so I'm trying to see whether the support is exceeding 1, 2, 3, 4. Right? It uses something outside. This guy's good, needs no reduction. This guy's good, support 2, 3, 4. This guy here, you've pushed it a bit too much. Now the support sees a 5. It's exceeded the bounds, so it will actually end up inside the ideal of quasisymmetric polynomials. Okay? So if your forests are pushed too far to the right, they are inside the ideal. So there's a transition happens. Questions? Okay, so 13 minutes or so. Let me see. Oh, so I've told you how to reduce forest polynomials modulo QSIM. The other thing I was interested in was principal specializations. So here's a result that tells you that principal specializations of forest polynomials are nice. You count decreasing trees. When you specialize, if your forest is exactly of this sort, then you can specialize all xi is equal to 1. Turns out you're counting linear extensions again. And so this is computable by a hook length formula. So you can give a product version, and you know the all one specialization of any forest polynomial. So right here, here's a forest polynomial supported on 1, 2, 3, 4. There's 3 linear extensions for this tree, 3 decreasing labelings, and there's 3 monomials that appear in this expansion. So I can specialize all xi is equal to 1 fairly easily. So where am I at right now? I wanted a basis which had 2 nice properties for my purposes. One was friendly in regards to reduction modulo QSIM, and second, good principal specializations. And I hope that I've ticked both of those boxes. I want to apply this to Schubert polynomials. Right? My end goal was to compute the divided symmetrization of Schubert polynomials. So that is what remains to be done. Once I express it, Schubert's in terms of forests, and then reduce modulo QSIM, things whose support exceeds n minus 1 are going to die. Things whose support doesn't exceed that are going to survive. And then I specialize all variables equal to 1. Okay, so I'll try and tell you this via a correspondence, which is actually a lift of the parking procedure I told you about. Okay, so here's a correspondence, an insertion algorithm between words and labeled forests. I'm going to take a word and cook up 2 symbols. right? This should feel like RSK. There's going to be a P symbol and a Q symbol. And the forests are going to be labelings of indexed forests. So I'm going to insert that word left to right and get 2 symbols. So what's the idea? The first 5, you sort of imagine dropping a particle along this line, and the particle drops as far as possible until it's able to pick up 2 children. Remember, the crosses are the leaves, and those could be children. So the first 5 drops right here and picks up this leaf and this leaf as its progeny. That's my first step. So I remember the label, that's the 5. I remember this is the recording tableau, if you will. That's the 1, because it's the first letter. Similar deal with the 8. Right? The 8 drops along this direction and ends right here, and I've recorded the label and the position. If you've seen heaps of pieces in the sense of VNO, this algorithm is essentially a modification of VNO's heaps of pieces. The next word is the 3. So no drama so far. That's the result of inserting the first 3 letters. Then comes the 9. Right? In theory, you want to imagine the 9 falling here and picking up these 2 as the children. Notice that this guy is already taken. So it can't drop all that far. It has to stop 1 layer above. And that's where it ends up. And now you can see that I'm building this tree. The next 4, well, in theory, it would have liked to pick these 2 as children. It can't, so it picks up whatever else it has access to. And those are those 2 root nodes. That 3 falls again, picks up whatever's closest. Okay. So I've constructed 2 labeled indexed forests. What's special about the labels here? They are decreasing in all directions and go from 1 through 6. That's a standard decreasing forest. What's special about this guy? Well, it increases to the right and weakly decreases to the left, in fact. So it's a local binary search forest. So this is my P symbol, and that's my Q symbol. Let me straighten the edges so that it feels 45 degrees. That's my P symbol. That's my Q symbol. And this is my theorem then. So joint with Philippe, the map taking words to their P and Q symbols is a bijection between words and ordered pairs P and Q, where one guy is what is called a local binary search forest, and the other is a standard decreasing forest. Okay, and this is also not jargon that we came up with. Local binary search forest show up in work of Gesell and Stanley in the context of hyperplane arrangements in the mid-90s, and in work of Alex Postnikov as well. Right, so now I have a bijection, and I'm just going to do the naive combinatorial thing. This correspondence induces an equivalence on words. I'm going to call 2 words omega equivalent if the P symbols coincide. So the P symbols coincide. I'm going to declare 2 words to be equivalent. So here are my equivalence classes for the set of reduced words for that particular permutation. Okay. So these 3 will all give me this tree. This singleton guy is going to give me this linear tree, and these 4 are going to give me this forest. Notice the support. 1, 2, 3, 4, 1, 2, 3, 4, 1, 3, 4, 5, and 5's exceeding 4. So what am I trying to say? The set of reduced words is closed under omega equivalence. So it decomposes into equivalence classes. Each equivalence class has an attached shape to it. Look at its P symbol, forget the labels. That's what's happening right here. Okay, so here's the theorem which tells you how to expand Schubert's into forest polynomials. Take your reduced words. It's closed under omega equivalence. Splits into equivalence classes. Each class has an attached shape. Sum the forest polynomials of that shape, and out pops the Schubert polynomial. So forest polynomials sitting coarsenings of slides, Schubert's coarsenings of forest polynomials. And I want to add that the well-known expansion of a Schur polynomial as a sum of fundamentals is hiding inside this. Okay, so this is a generalization. If you were to pick Grassmannian permutations, your trees have this zigzag feature. So the posets that you're trying to cook up, they're attached p-partition generating functions are actually fundamental quasisymmetric polynomials. So the expansion of Schur into fundamental is a particular case of this particular expansion. Yes? No, they can have multiplicity. Different reduced words can end up giving a different labeled tree, but the same underlying unlabeled tree. So this is not a multiplicity-free expansion. So same forests can occur with multiplicity. So that's sort of misleading. All I'm saying is, in the same way that I was indexing slides by words, different words could give the same slide polynomial. That's sort of what's happening here. Sort of easier to write down. Other questions? Yes. In the shadow. If you did not care about what was happening at the level of the trees, you only wanted to see how the support was growing. You know those marked spots? Those are actually tracking where's the root. Okay, so you take a shadow of that tree algorithm, you just observe what's happening on the integer line. That's where the parking algorithm's happening. Yes? So if the intervals merge eventually to become one single interval, that's like trees coming together and getting a single root. Okay? Yeah. Other questions? 4 minutes. Let me just go back to my previous example. Here's 21543. That Schubert polynomial has 14 terms. It's a sum of 3 forest polynomials. I'm indexing using the codes of each forest. This contributes a single monomial. This contributes however many, it contributes 3, and this contributes x1 times a fundamental quasisymmetric polynomial in the variables x1, x2, x3. So it's a total of 10 terms, and 10 plus 1 plus 3 is 14. So that Schubert decomposes as such. I want to reduce modular QSIM. Given what I told you, forget one of these guys, right? The thing splits. The moment you have multiple components, don't care. So those two survive. So modular QSIM, it's 2 forest polynomials. I'm specializing all ones, count linear extensions, 4. So that's sort of the story. You first expand into Schubert's, ignore certain forests that have too much of a support exceeding bounds. The remaining count linear extensions. That's hook length formula. Put a bunch of stuff together. That's the answer. So long story short, the final proof comes down to this single slide. Schubert's, Billy-Jokush-Stanley, coarsen-it, forest polynomials, separate them according to their support, ignore the red stuff, take this stuff, specialize to all ones, count linear extensions, turn this into a parking algorithm. That's it. Right, so let me see. I don't want to take time. I just want to tell you some things that we can do and some things we wish we could do. So what else do we have? We can multiply these non-negatively. Sort of motivates looking for some geometric explanation. I don't have one. I can actually tell you how to expand monomials into forest polynomials. Turns out the coefficients are all 0, 1s, and -1s. We have what would be called harmonics for the ideal of quasisymmetric polynomials. These turn out to be volume polynomials for certain cubes in a subdivision of the permutahedron. So those are things we can do. We have a product rule, but somehow it's so bad that it doesn't tell you that Monk's rule is multiplicity free. So we conjecture that Monk's rule is multiplicity free. And finally, there's 2 combinatorial puzzles. I gave you a non-negative interpretation. Actually, this thing is strictly positive. And that comes from another formula for the A sub W's. The problem with that formula is it's a sum of rational numbers. So it's positive because it's a sum of positive rationals. But that doesn't tell you it's integral. So I have non-negative integral or positive rational. And I'd like to have some combinatorial explanation for why it's strictly positive. And then there's a symmetry, which the parking procedure somehow doesn't explain. Right? A sub w is equal to A sub w inverse. I would like to see it at the level of this parking procedure, inserting reduced words and occupying entire intervals, and it's not clear. Okay. Thank you. Thank you. Yes.
Okay. Yeah. Well, no, way
Oh.
earlier than this, where you were. I don't know if it's important to find the slide, but where you were summing over only those reduced words that were omega parking. How? Yeah, that's the one. How likely do you think to find or how difficult is it going to be to do a K-theoretic version of this?
I wish I had something wise to say to that. Off the top of my head, I don't have anything immediate to. So you're saying turn everything here into its K-theory equivalent, and what's going to be the?
So I'm asking for the K class of the permutahedral toric variety. Sure.
I'll have to think. Off the top of my head, no clue.
All right, question 2. So there's this paper by Smirnov and Tutabalina that thinks about the the expansion of Schubert's into slides and says you can think of the Schubert as this sum over facets of this pipe dream complex and the slides, and that's a ball, and inside there the slides form these sub-balls. Do the forests, does the decomposition of the Schubert into forests, is that also into intermediate sub-balls between the big ball and the little slide balls?
So that decomposition of Smirnov and whoever was the second person, sorry, it uses certain commutation moves on the S sub i's to generate the balls, right? So the facets.
Yep.
And our equivalence relation refines the commutation. So I said that reduced words, class of reduced words is closed under omega equivalence. There's a finer statement. Any commutation class is closed under omega equivalence. So maybe there's the likelihood that you could assemble. I don't know if the eventual thing will turn out to be a ball as well. So something I would do then. Yeah.
Okay.
Thank you.
Third question. Your correspondence between words and pairs P comma Q, is there a growth diagram picture to go with that?
Don't know. I mean, I sort of have tried to phrase a bunch of our results with like pipe dreams and more conventional, but somehow for bookkeeping and tracking purposes, stuck with the trees at this stage. So all your questions are great questions. I don't have much to offer just yet, but I'm recording them.
Okay. Thanks.
Yeah. Oh, so the key stuff is sort of, yeah. So I tried expanding one into the other, and there was, sorry, so Oliver's question was how do the florists compare to key polynomials? And no transition matrix looks particularly nice. Yeah. I wish, no, I don't know. That is one thing I would like to understand better. So here's something, so if you look at the polynomials, modulo quasisymmetric polynomials, you look at the Hilbert series, it's not palindromic, like it has Yeah, it's log concave and all that, but it doesn't have this palindromic structure that you read it. It won't be smooth. But so let me attempt an answer which I have currently, but it's not a good answer. So here's the thing: the permutahedron has a very specific cubical subdivision into combinatorial cubes. Every combinatorial cube determines a toric Richardson variety. I can write its cohomology ring as a polynomial ring modulo some ideal. Turns out the intersection of all possible ideals as I go over the cube is the ideal of quasisymmetric polynomials. Now, I don't know how to translate this information into answering your question, but there is some intersections of ideals that correspond to cohomology rings of cubes as I go along my cubical subdivision. There's Catalan many cubes, Catalan many ideals, I intersect them, I get the quasisymmetric polynomials. But yes, this is not stuff we've written up, but this is what we've observed. I don't know how to, I don't think I don't have the qualifications to turn that into a good answer, but that's the one I have. So all I know for the moment is that there's a cyclic group action on the polynomial ring modulo quasisymmetric polynomial. That's not obvious from the definition of quasisymmetric polynomials. So Z mod NZ acts, so the variables can be permuted, and they can be flipped. So there's a dihedral group worth of symmetries in this quotient. We understand the cyclic action to some extent, but no, not really. I don't have a particularly good answer to your. I think the upshot is I don't have good answers to any question, but the great questions overall. So, Sammy, yeah. Ooh.
You know, Hagelin, Lowoto, Mason, and Van Milligenberg have these quasi-symmetric Schurs, which live between Gessels and Schurs. And so there are now, like, I don't know, 10 different ways of thinking of these, or 10 different versions of them. They're like the young ones and the left ones. And there's there's non-symmetric analogs, like the quasi-keys that Dominic and I have, but there are a bunch of others now. So do your forests decompose into that? Because those still live in the quasi-symmetric space, unlike the de Mesure characters, which are not quite in the same realm. Do yours play nicely with any of those bases that you know of?
So I tried a bunch, and what I've reported here is perhaps the nicest thing that happened. That slides, forests, Schuberts, monomials.
So none of those other ones.
Yeah. So okay. Keys would have been nice, but that doesn't work. Like the nil-plactic relation and the omega equivalents don't exactly gel well. But maybe what Alan suggested with coarsening the Smirnov to Tubolina.
It's just a different direction. That's
yeah.
Very interesting.
So yeah. Alan, did you have? Yeah.
Instead of taking polynomials, modulo, positive degree, quasi-symmetrics, have you looked at tensoring together two copies of polynomials over quasi-symmetrics?
No. Sorry.
So if you take polynomials modulo like elementary symmetrics, that's going to get you cohomology of the flag variety. If you do this tensor product, I'm saying it gets you equivariant cohomology of the flag variety. So a double version of what you...
So this is something I was asking Oliver. I'm like, if I wanted to double some of the stuff that I was going to talk about, how would I go about? So
yeah, that's how.
Okay. Yes. Sorry, I'm doing the, whoever's the MC should stop me from... Yeah.
Does what you are doing here, can this be extended to stellahedral variety?
No clue. I know of the work that you're talking about, so let me make up in some manner. So the answer that I didn't give you involved mixed Eulerian numbers. If I can get this guy to wake up. So let me. All right, so the answer that I didn't give you involved mixed Eulerian numbers, Mixed Taulerian numbers you can compute mixed Taulerian numbers in the Chowring of the permutahedral variety. They compute mixed volumes. So this is the answer I didn't give you. A sub W has a rational expression as a sum of mixed Taulerian numbers, which are mixed volumes of hypersimplices. And that is a computation you can perform in the Chowring of the permutahedral variety. Recently, Eric Katz and Max Cutler have matroidal mixed Taulerian numbers. So this would correspond to the uniform matroid case. And you can start playing linear combinations and dividing out and computing integers in that manner as well. But I don't know if the stellarhedral variety would fit in that context. So there's matroidal analogs of some of these results. Eric Katz and Max Cutler put a paper out late May.
So is there a way to stabilize your expansion, sort of like dropping the flag condition, like that kind of stuff?
Or allowing myself labels in the negative side, right? Imagine your trees. I stuck with the positive side. So all of these become series in the backstable sense. The slide becomes backstable slides, if you will. Backstable Schuberts expand into. So the combinatorial results translate. But there's a lot more in the backstable Schubert picture, which is the geometry side of things, multiple variables. That stuff I don't have access to or don't understand well enough to say anything.
Okay, so after the back stabilization, you're getting another expansion formula probably, right?
So you get a series, right?
Yeah, yeah.
If you were to look at it, it lives inside QSIM tensor polynomials in X. If you apply your maps from Lamb-Leishman-Mazono, eta 0, you would get a fundamental expansion which remembers the p-partition generating function of that tree poset. If you apply pi plus, you remember the polynomial part, and then I can express it in terms of sums of fundamentals times forest polynomials. So that stuff is doable. What does it mean in the geometric sense? I do not know.
Great, thank you.